Thank you, Karin, and thanks for the invitation. Just going to set my timer so I don't get over time. Well, yeah, Karin just nicely read my title for the talk. Really, it's just an excuse to talk about one of my favorite things, which are cluster algebras or cluster combinatorics of infinite rank. And what I'm going to start with is a type A cluster story. And I'm very sorry we missed Emine's talk, because I think with Emine's talk, we would have had the perfect setup for this, but I'll have to do without that. So we're going to start with a classical finite rank setting. And one of the very early and very important examples of a cluster algebra is the Grassmannian cluster algebra of type A. So this has already been introduced in the very early papers on cluster algebras by Fomin and Zelevinsky. There's also a lot of famous categorifications, additive categorifications to go with that picture. The very famous one by Marsh, Reinke, Wright, and Todorov, and by guys Leclerc and Schröer. I'd also like to point out the categorification of Grassmannian cluster algebras by Jensen, King, and Su. One really nice feature of that categorification is that they draw a connection between two very important examples of a famous ADE classification, namely between the ADE classification of finite type cluster algebras and the ADE classification of simple plane curve singularities. Now, if we just think of these cluster combinatorics from a purely combinatorial viewpoint, we can encode this in the combinatorics of a regular n-gon, where we consider arcs and triangulations of this regular n-gon. Now, as I've alluded to, what happens when we take that to the limit, when we take n to infinity? As far as I'm aware, the first work on that has been done by Holm and Jurgensen on the categorical side over here. So Holm and Jurgensen describe a very natural category from an algebraic viewpoint, which exhibits cluster combinatorics of infinite type A. I also mentioning Igusa Todorov here, who took that idea and vastly generalized it to kind of get a holistic approach to what it should mean, what a infinite type A cluster combinatorics should mean, or cluster category should mean. Now, Holm and Jurgensen show that on the combinatorial side, their categories have natural cluster structures that are associated to triangulations of an infinity gon. And by infinity gon, we just mean the line of integers, which I draw in a fancy way on a circle here, because of hopefully what will make sense shortly. Now, what happens in the middle here is we started in joint work with Jan Grabowski. So we introduced the notion of a cluster algebra of infinite rank, which is what we get when we allow infinite clusters, still only finite but arbitrarily long mutation sequences between them. And what we get out here, I'm telling a little white lie here, because we could also get rings out that look a little bit different, but essentially we get rings out that look like infinite versions of our Grassmannian cluster algebras. So these are in particular co-limits of these rings up here. And they're not just co-limits as rings, they're actually co-limits in a cluster theoretic sense. So this is formalized by our result that actually any cluster algebra of infinite rank you can view as a co-limit of cluster algebras of finite rank in an appropriate category. And the appropriate category here is the category of rooted cluster algebras, which was introduced by Assem, Dupont, and Schiffler, and which is, as far as I'm aware, up to date still the only attempt at a category of cluster algebras. Now, once one starts studying these infinite type A cluster combinatorics, it becomes apparent that there are some limitations in this picture. Namely, if we just look at the combinatorial side over here, what about arcs ending in an accumulation point? Also, more subtly, not all triangulations are connected with by finite sequences of mutation anymore. So how does one go about fixing that issue? And on the combinatorial side, this has been done in joint work with Karin Bauer and independently by Giannacci and Felixson, which leads us to consider triangulations of infinitely many marked surfaces with accumulation points. Now that, of course, ties in with what Emine would have told us, which is that on the categorical side, this has been studied by Paquette and Yildirim, who took these Igosa-Todorov, the discrete cluster categories, and completed under these infinite arcs. Independently, Tom Fisher has also looked at that in the one accumulation point case. Now, what should happen in the middle here is still a bit open. So there is two notions of these completed cluster algebras that I'm aware of. One by Giannacci and Felixson, coming from triangulations of infinitely marked surfaces. One by Paquette and Yildirim, coming from these type A cluster categories, but no intrinsic formulation of what a completed cluster algebra should be, just from a description as a ring. Now, first, I'd like to convince you that actually this is a natural question to ask, not just in a type A setting or in a surface setting, but more generally. And that leads us to Grassmannian categories of infinite rank, which also tell us that actually what's happening here really is a very natural thing to look at, also from an algebraic viewpoint. And this is joint work with August Zhang, Faber, and Schroll. And we introduced these Grassmannian categories of infinite rank, which are categories associated to a hypersurface singularity that looks like this. So we study graded maximal Cohen-Macaulay modules over that guy, and that gives us something that really looks like a Grassmannian cluster category somehow. So this is based on the following statement. If we look at a suitable subcategory of this guy here that we can naturally describe intrinsically in this category, then this encodes the combinatorics of these Grassmannian cluster algebras of infinite rank. So which, as in the case k equals 2, we can view as co-limits of finite rank Grassmannian cluster algebras. So this is one side. So it sees these this tranche in between here, that one. But what is more, it also sees that stuff here. So if we look at the whole category CK, then this also sees the infinite arcs, and I put that in quotation marks because a similar thing happens for higher k as well. Now for k equals 2, this really aligns with what we know about type A. So namely, if we look at k equals 2, then if we look at this category, so this is the subcategory of generically free graded modules in this category of graded Cohen-Macaulay modules. The stable category of that subcategory is equivalent to the Holm-Jurgensen category, which is the same thing as the Igusa-Todorov category for one accumulation point. And if we look now at the whole category, the whole Grassmannian category, in the case k equals 2, this is actually this completion that Paquette Yildirim end up with. So it's not just a natural question from a combinatorial perspective to complete these discrete cluster categories, but these are actually categories that extremely naturally show up when we consider questions from algebra. Now, to just give a bit of a teaser as to what to put in here, and that is based on joint work with Christian Korf and our PhD student Damien Wierzbicki. And it looks like, so I kind of kept saying co-limit for this middle tranche of the picture. It seems like when we want to look at completed cluster algebras, what we should be looking at are inverse limits. So it seems that the natural environment for these completed cluster algebras are inverse limits of cluster algebras in a suitable category. And that's going to be a category that's slightly different to the Assem-Dupont-Schiffler category, because instead of gluing on, we should be thinking of cutting off. So that's kind of the slogan. Doing that, setting it up like this in terms of inverse systems will then allow us to define these completed cluster algebras in terms of inverse system of clusters and inverse systems of mutations. And yeah, hopefully give a good intrinsic description of this gap here in the middle. So thanks for your attention.